We are Group 13, and this is our project DoorVision, a facial recognition home security system. On our team is Leisha Antonor on software, Dawson Beach on hardware, Kalani DaCosta also on hardware, and Evan Scoff on software and our team lead. We designed DoorVision to provide a convenient but effective home security device, since less than half of Americans own any type of home security system. Our project is made up of two parts: a physical device to be mounted on a standard front door, and a mobile application used to monitor and control the device. DoorVision works by checking every face that approaches the user's front door. If that face matches a Face ID stored in the device's database, it unlocks the door. Otherwise, the door remains locked. The door can also be unlocked through a keypad code. To use DoorVision, first the user must scan their face through the mobile app using their phone. After the face is logged into the system, whenever they approach their front door, it will automatically unlock by triggering a servo motor to turn the deadbolt.
For our MCU, we chose the ESP32P4M3 module. The ESP's RAM and clock speed allow for quick face recognition and support high resolution camera processing at about 30 FPS. This MCU also comes with light and deep sleep modes. Our project would utilize the light sleep mode since the system will need to be continuously running for multiple weeks before recharging. As part of the hardware system, we're using the IMX219 camera module with an 8 megapixel resolution. It has strong performance in low light environments and will be used to record and scan faces as people approach the door. We're also using the OPT3001 light sensor paired with an eye safe white LED used to illuminate the area in front of the door during the night or moments of low visibility. Next, we're using the VL53L1X motion sensor, which plays a large role in power management since it's responsible for waking the system from light sleep mode and sending it back into sleep mode. The motion sensor also has its own low power mode. In this mode, it can detect up to 4 meters. While the entire system is in light sleep, low power mode, if the motion detector is tripped by sensing motion within 3 feet, it will wake the entire system in time for the user to seamlessly approach the door and unlock without delay.
A simple 10-digit keypad is also implemented as a backup to the facial recognition system. If the camera system should ever fail or the user wants to unlock the door without scanning their face, the keypad will also trigger the servo motor to unlock the door. Next to the keypad is a RGB LED to display the unlock status to the user. A 3D printed enclosure will be used to house all of our components. The enclosure consists of three parts: the exterior main enclosure, which includes a back piece, and the interior deadbolt cover. Our initial enclosure had some errors, which includes the keypad buttonholes being too small and the main enclosure being too narrow. The second iteration fixed these issues by inserting a bigger hole for the entire keypad to fit and widening the main enclosure. A mobile app is used for remote control of the system. The app's features include a live camera footage, management of authorized users, remote locking and unlocking of the door, and an activity log. The app utilizes Swift, which is Apple's native coding language. Swift was chosen for its excellent hardware integration, real-time performance, and its security features such as Face ID and Touch ID. Our system communicates with external hardware and requires a language that can store and process data in real time while maintaining performance.
To demonstrate the functionality of this design, 3 separate videos along with screen recordings from the mobile app will be shown. First, a video of a user registering their face on the device. Second, a video of a registered user successfully unlocking the door and an unregistered user attempting to unlock the door and failing. And third, a video of using the keypad as an alternative form of entry. Here we have a video of a user enrolling on the mobile app. To enroll, they'll select the Enroll User button on the home screen, which will bring them to the page you see on the right. First, a user types in their preferred user ID. Then the app prompts the user to slowly rotate their head around the camera so the camera can capture their face at multiple angles. When enough data is collected from a specific angle, the LED will flash green. After 6 green flashes, the enrollment process is complete. Next is a video demonstrating how the device responds to a registered user. You can see the LED initially flashes red since it's not confident in who the user is, but as the user approaches, it quickly flashes green, indicating a successful unlock. Here is a video with the locking mechanism attached. It's worth noting that this video takes place during testing, and as a result, the deadbolt initially extends when it should retract. This is reverted back to normal in the live version. Here is a short video of what happens when an unregistered user approaches the device. The LED flashes red, showing that the device doesn't recognize the face. On the right is what the user on the app would see when viewing the live feed, and displays of the console logs showing that the system has seen an unknown face. Finally, we have a video of a user entering a keypad to unlock the door. First, an incorrect code is entered, indicated by the red LED flash and keypad incorrect text on the device log. Then, the correct code is input as shown by the green LED and unlocking text on the device log. For this demo, we highlighted 3 of the key engineering specifications for this project. The facial recognition system should on average have a confidence level of 65% when scanning a known face. The motion sensor should accurately detect movement at least 3 feet away, and the night light LED should activate whenever the light sensor detects light levels below 25 lux. Here are 3 out of the 10 total tests done to validate the facial recognition confidence interval. During this first test, we use an old user ID that was scanned in during different lighting. As you can see, the system initially has a hard time recognizing the user in these new lighting conditions. The system displays unknown user because even if the system is 64% certain, it won't give the go-ahead to unlock the door unless 65% certainty is achieved. However, after roughly 20 seconds, the system is able to confidently recognize the user with a 70% certainty. In test 2 and 3, we have re-registered the user under these new lighting conditions. Both tests show the door unlocks almost instantly, both with confidence levels above 65%. Next is the motion sensor tests. During these tests, we laid out a tape measure and slowly approached the device until the motion sensor triggered the device to wake up. This is indicated by the LED flashing blue. It can be difficult to see in the first 2 videos, but will be highlighted closer in the third test video. Once the LED turned blue, we stopped and measured the distance away from the device to test accuracy. To test the light sensor, we slowly covered the sensor until the white LED turned on, as shown in this first video without the 3D printed case. The same experiment is shown in the second video with the 3D enclosure as a proof of concept. These are the results from the 10 confidence and 10 light level tests. During the confidence test, we only measured values that were enough to trigger the system to unlock the door, meaning values over 65%. Despite this, we saw that a majority of tests had confidence levels significantly higher than 65%, with the max being 71%. The average confidence level was roughly 68%, meaning the system exceeds the requirement. The average lux level that triggered the white LED to turn on was 22.15. Since this is below the 25 lux requirement, this system also passes. To improve its accuracy, we could increase the sampling rate of this sensor to bring that number closer to 25. However, in a real-world scenario where the sensor is observing slow light level changes due to the sunset, the average turn-on time would be much closer to 25. Lastly are the results from the motion sensor tests. Since we measured with a tape measure, we rounded each measurement to the nearest whole inch. Converting those measurements to feet, the average distance that caused the system to wake from sleep mode was 2.58 feet. Since our system is turning on nearly half a foot too late, we should slightly increase the turn on distance from the sensor to give the system plenty of time to wake from sleep. Despite this, the system still meets the requirement of turning on at distances less than or equal to 3 feet, since there were no times it turned on further away. If the system incorrectly turned on due to the movement in the distance, for example, someone passing by on the sidewalk in line with the sensor, it would slowly drain the battery even when the system isn't actually being used by the user. Thank you for watching the final demo video for Group 13 DoorVision.